Hello everybody and welcome to this SimScale webinar. My name is David Short and I'm going to be instructing you, showing you the platform and going through this topic with you. Now today we are looking at non-linear material properties in FEA. So this is going to be an FEA based webinar, and very kindly we have done this, very kindly one of our customers, Explotechnik AG, have collaborated with us for this webinar. So the simulation that I'm going to show you today has been provided by Explotechnik AG. So they provided the model and the setup, and we've run it from our end. So what they've been doing is they've been utilizing some of the new features that SimScale has in our FEA. And so I really want to share that with new potential customers and some of our older customers as well. So yes, welcome to everybody, and I hope you enjoy the webinar. So a little bit about me. My name's David Short, and I was originally with marine engineering. So that's what I studied, and so that gave me a pretty good knowledge of both fluid and solid mechanics. Now I've had professional experience applying these kind of numerical techniques and also teaching them. So the agenda for today, we're going to be looking at the benefits of simulation and then also the benefits of using specifically SimScale for your simulations. And then we're going to be getting into today's topic, which is structural analysis using nonlinear material properties. So simulation, why do people want to simulate? To avoid physical prototyping and very costly experiments, the simulation industry has been developed to reduce the costs and to be able to perform those experiments numerically. So using both FEA and CFD software to perform, for example, wind tunnel type experiments, or also to be doing structural testing, all numerically. So this really reduces the time we need for our design processes and helps minimize lost costs and also to highlight possible risks of a design. So if we do simulation and we see that there are pain points in the design, we've caught them early, and it means that the physical models haven't been created yet. So actually we're saving ourselves a lot of time and accelerating that design process. Now SimScale has taken a bit of a different approach to simulation. We've tried to break down those traditional barriers to entry to simulation, which are namely that for traditional simulation software, you require large, high power computers, and you normally need a lot of training to be able to actually use these software that have been developed for people with PhDs and who are specifically in that field. We've taken a completely different approach by implementing our simulation software as a web-based application, which is utilizing cloud computation. So all the heavy lifting of our simulations are actually done using cloud computing. And this means that actually we can run very high power, highly accurate simulations using just a bog standard 2-core laptop. So the idea of this is to really allow people to, from any field of work where simulation would be of benefit to the company, people without experience and people with who are just interested in getting insight into their designs through highly accurate numerical techniques. SimScale provides a easy to use and cost efficient solution. So SimScale is an all-in-one, it's a generalized tool that covers both structural analysis, CFD, and also thermal analysis. So we're in our structural analysis, we're looking at statics, dynamics, thermomechanics, and then we're moving into the CFD world of incompressible, compressible, and also looking at both convective heat transfer, conjugate heat transfer, and yeah, so that's basically our CFD and FEA, and we've also brought in some really exciting new solvers based on the lattice-Boltzmann method, which are used primarily by us to look at external applications. For example, wind comfort. A lot of our customers are looking at their wind comfort type applications, and they're getting a lot of use out of our new LBM solvers. So it's a secure platform, cost efficient, easy to use. So we have real-time support, which allows the customer to really engage with us in a live interactive manner. So it's not like traditional software where you would apply for a support ticket, and we're there to support you live and teach and recommend how we would maybe suggest it for you to do your simulation. Now, another part of this learning process is the collaboration of using our community. So I'll show you when we jump onto the platform how you can have a look at other people's public projects and learn from their simulations and really get a good impression of what our customers are utilizing the platform for. Now, this is an FEA webinar, so I wanted to touch quickly on the specific applications that we do offer. So with our static stress, with our statics dynamics, we offer both linear and non-linear functionality. Now, non-linear is where we're going to be heading in the next few slides, but just to give you a good impression of everything that we can do, our dynamics includes both eigenmode type simulations to find the natural frequency of your structures, and we also offer both transient and frequency domain response analyses. So we can look at harmonic analyses and also direct transient analyses. So a few examples of what we do use the simulation for. Starting from the top left, we're looking at the nonlinear stresses leading to buckling or some phenomena like this of a gantry crane. To the top right, we're looking at a snap fit mechanism. So this includes a non-linear type contact, and this is something that we can handle easily on the platform. So that's a non-linear static type analysis. When we move into dynamics, we can look at things like drop testing, for example, of this drone on the bottom left. That's using a direct transient simulation to have a look at the impact forces and stresses on the drone arms as the drone hits the floor. Now, as I mentioned earlier, we do have thermal capabilities in our FEA solvers as well. So we can look at thermal shocks, for example, in this valve. You can look at the thermal shock, which is very highly related to what we're going to be doing today. And so that's coupling the thermal solution, so based on conduction. Then we're going to look at how those thermal levels, so the temperatures, actually affect the mechanical stresses in the mechanism or the device or product. So yeah, if we go from full applications, we're going from static to dynamic and then up to frequency based response analyses as well. So a little bit more on non-linearities and what we can really offer in the platform. So a bit of background. A linear, if we're talking about statics, a linear simulation is one in which the stiffness matrix remains constant through the full length of a simulation. Now, for a non-linear type simulation, that stiffness matrix is actually going to change as the simulation progresses. So reasons why this would happen are that we've got three reasons why this would happen. So firstly, that the material properties actually change as we increase the strain or the stresses on the model. So we might move into the plastic region, which then means our stiffness matrix is going to change as the simulation progresses. So when the material properties change, the stiffness matrix changes as well, which means it's a nonlinear simulation. We'll have to run it nonlinearly on the platform. And the same goes for a large deformation in a simulation. This large deformation is essentially changing the structure. So the stiffness within that structure is going to change. So the reference frames actually change for the structure, which means that the stiffness matrix will change, and therefore we're going to have to run it non-linearly. The same goes for physical contact. So when you have a physical contact, you're going to allow for two parts that were perhaps separated to come into contact. Now, when they come into contact, they're going to take some of the stiffness from each other. So some of that load or stress is going to be transferred between the two objects, therefore changing the stiffness of the overall model. So with these three types of nonlinearity, we can handle simulations using the SimScale platform. Now today's topic, we are specifically looking at material nonlinearity. So the first that I mentioned from the three nonlinearities that we cover. So what are the material nonlinearity phenomena that we're talking about? So you could have materials that behave plastically above a certain strain. So then they plastically deform, meaning that deformation is actually going to remain deformation. It's not going to spring back like it would in the linear elastic region. So when we get into that plastic region, the properties of the material have physically changed. Now the same goes for hyperelastic. It means that within the elastic range, the relationship between stress and strain is not linear. It's actually so hyperelastic means there's going to be a non-linear relationship within that elastic range, but it's still going to, if you deform it, it's going to come back to its original position. Now what we do offer is temperature dependent properties. So if we're doing a thermomechanical type simulation, the properties will change with the temperature in the simulation. So the density of the materials is going to change, the conductivity may change, and the specific heat may change. And we can implement all of that on the platform. So you would say you would give a table of the different properties at the different temperatures, and then that would be taken into account during the simulation. Now what I really want to highlight today is the fact that we have now implemented temperature-dependent plastic stress-strain relationships, which means that we can essentially upload multiple stress-strain curves for the different temperatures that are going to be seen during the simulation. So as a component heats up, the stress-strain relationship is actually going to depend on that temperature. And so we'll get into that a little bit more in just a moment. But that's the new feature that we're really excited about, that we've implemented successfully. And that is what Explotechnik AG, the company that we've been collaborating with for this webinar, have been utilizing for their simulations. So a little more about this. So Explotechnik, they do really cool things with combustion chambers and looking at the thermal stresses and the mechanical stresses within these combustion chambers during experiments and the operation of these chambers. Now, the setup and the geometry, as you can see on the right, has been really kindly provided by Explotechnik. And yeah, so I've been in contact with Rito. We've been working a lot over the last months. And they've been utilizing a really large range of SimScale's capabilities. So they're looking at both nonlinear statics, like we're looking at today, and they also look at dynamics and also the thermomechanics. So we're looking at nonlinear thermomechanics today. So the setup for our simulation, when we use the simulation, the SimScale platform, it follows the same approach as all simulation type applications. First, we need to upload our CAD, and then we need to create our simulation setup. So that's going to include creating a mesh, applying boundary conditions, and the simulation controls. And once we run our simulation, we can then make our design decisions based on those simulation results. Now I'm going to show you that whole process today based on this combustion chamber. So the model provided, I've cut it in half just so we can have a look at it. On the inside, we've got a brass piece sort of rimming on the right-hand side, and then we've got the rest of the structure made up of S355 steel. Now, this steel is what we're interested in today. The guys over at Explotechnik, they know that this steel behaves differently at different temperatures. So they wanted to utilize the temperature-dependent plasticity functionality that we have at SimScale. So a little bit more about those materials. As I was mentioning, we've got the plastic behavior of the steel, which is temperature dependent. And then for those who are really interested, those are the densities, conductivities, and the other properties of our materials. Now we don't need to go into detail about that, but I wanted to just show you the differences between our materials that we're using. So with the stress strain behavior, we're looking at linear elastic for the brass, and for the steel we're looking at plastic temperature dependent. stress strain behavior. So here is the material data provided by Explotechnik. So they've measured the stress strain relationships for the material at different temperatures. Now these are really basic stress strain curves, only using 2 points. So bilinear type curves. And for these curves, we've been given a yield point and then an additional data point, which is normally the ultimate tensile strength. Okay, so as you can see, the steel exhibits different mechanical behavior as the temperature changes. So down at the 573 Kelvin, we're seeing a very different relationship to the, or a different yield point to the material at a lower temperature. So the way we would implement that on the platform is as a table upload. So you can see on the right here where I've highlighted in blue, that corresponds to the first curve that's in blue on the left. Now we're only providing the yield point and the ultimate tensile strength or any additional data point for our bilinear curve. Now you can obviously have stress strain curves with as much detail as you'd like. So instead of just having 2 points here, you could have 100 points. After the yield point, you'd then have very detailed description of the plastic behavior, the stress strain behavior. But for this webinar, I just wanted to really make it simple to understand how we implement the different properties at different temperatures. So our first column is the temperatures. So we have 2 points for our blue curve. The yield point is the first, and then the UTS is the second point here. And the same goes for the other 3 temperatures. Now, between these temperatures, the solver linearly interpolates the stress strain curves. So it's not as though we can only simulate at these 4 temperatures. We're going to be able to simulate at any temperature, and it's going to linearly interpolate, and on the far sides, it's going to extrapolate linearly as well. So the loading of the chamber, so this was provided, and as experimental data, so during their experiments, they measure what the thermal shock is on the internal of the combustion chamber. Now we can then use those experimental data points as our input for the thermal load on the structure. So as you can see here, we have a really steep gradient up to about 0.1 seconds. So that is the combustion, the experiment, and then once that the combustion is over, we immediately drop back to ambient input temperature. Okay, so that's not what we're going to see the structure behave as. We're going to see the increase of the temperature of the structure up to here, and then it's going to slowly descend. And now this is what Explotechnik are interested in. They're interested in seeing how the temperature is actually going to, of the components, how it's going to behave after the 0.1 second. So after the combustion, they want to see both how the temperature evolves over time and how the mechanical stresses also evolve over time. So the same goes for the pressure. So this was measured in experiments. We can apply that internal pressure on the surfaces internal of the combustion chamber. So for the purposes of explanation, I'm going to call these the application surfaces. So I refer to them quite a lot in the simulation. So anything on the internal of this combustion chamber, so everywhere where it's sort of green, and on the previous slide where it was red, those are the application surfaces. So we're applying the temperatures and the pressures to those application surfaces. So once we have our setup, I really want to show you actually on the platform what we can have a look at. So here is the SimScale website. If you haven't been on here, I really strongly recommend that you log in or you sign up, and then you can have a look around and check out some of the projects of our customers and users, and then you can really get a feel for how people utilize our software. So Here is the public projects page. You can go through any of these and take a look at the range of simulations that we offer. And yeah, so if something takes your fancy, you can open it, explore, and find out how they simulated it, what result outputs they got. And so this is why we want to collaborate with our customers, and we really all want to learn from each other, because it's a complicated field, and through collaboration we're hopefully going to learn a lot more together. So here is the simulation itself on the SimScale workbench. Now I've uploaded two different geometries, one full geometry and one cut in half. So I did my initial simulations on the half model, just because the mesh requirements are obviously going to be half. So if there are any problems, I can troubleshoot it much easier, because I can run my simulation much quicker. So that's a good troubleshooting technique that I tend to use. First, split your model, and then once you have something running well on a half model, then you can easily switch over to a full model as well. But I'm going to show you the full run. So with our geometry uploaded, the first thing we need to do is mesh it. Now we've got a brand new surface-based mesher on the platform, and this is it's really reducing our meshing runtime. So to create this mesh of 314,000 nodes, that only took 5 minutes, running on 16 cores, utilizing the cloud computing. Now you can apply as much levels of detailed refinement as you'd like to the model, but I was actually pretty happy with the mesh that came out of the automatic settings. So when we do have a look at when we do bring in models of multiple parts, so multi-body models, our FEA simulation is going to automatically bond together, or it's going to automatically detect any contacts between the surfaces. So here we can see a bonded contact between the end piece and the main body, and also we've got one between the copper piece and the other bodies. Now we're doing obviously a thermal mechanical simulation, so we need to enable heat transfer between the bodies. So over these bonded contacts, we're going to enable heat transfer. So that's just going to be a straight conduction through the bonded contact, as though it wasn't there. Now I'll just show you quickly where you actually go to find the simulation types. So next to simulation, you go on the plus button here, and the simulations that I was talking about earlier are all listed down here. So for this simulation, we're looking at a thermomechanical type analysis. So this includes both heat transfer and then the mechanical stresses induced on the model. Now this can be run either transiently or as a steady state solution. But as we have our loading as a time history, so we have that thermal and we have that pressure load as a time history, we need to run this simulation as a transient simulation. So under here we would go to transient, and so that's essentially making it a dynamic simulation, but it's not dynamic in the sense of needing to look at inertia. So we've put down the inertia effects to static, because we know this thing is not moving, it's not accelerating in different directions. It is stationary, but obviously our thermal load is transient. So we're going to run this as a transient thermomechanical simulation. And we do need to make sure that our simulation is nonlinear, so that then we can apply the nonlinear material properties to the steel. So when we jump into the material definitions, we've got brass as a standard material on the platform, and so you could go into our materials library, hit the plus button here, go down to brass, and hit apply, and then it's going to bring it into your simulation. For the S355 steel, I took the basic steel and then customized it to match the properties provided by Explotechnik. Now, under material behavior, we need to make sure it's as plastic. So we could have hyperelastic or plastic for our nonlinear material properties, and we're using plastic in this application. So as I showed you earlier, you apply the multi-stress strain curves at the different temperatures as a table, and this table is found just here. So that's what I showed you earlier with the blue and the different color stress strain graphs uploaded into the workbench. Now, when we want to apply, for example, the conductivity as temperature dependent, we could do that as well using a table upload. So just like we did for the plastic stress strain relationship, we could do that as well in the thermal conductivity if we wanted that to be temperature dependent. Now, Explotechnik didn't specify any temperature dependent conductivity, so we've kept this as constant. Now, in terms of boundary conditions, really applying the physics to this application, we needed to firstly constrain the model somehow. So these are the bolt holes at the top where it's connected and fixed to a base. Now, these are fixed support, so no translation or rotation is allowed on any of the nodes on these surfaces. So that's going to allow, because we've got bonded contacts between the different parts, this thing's going to be constrained in space. Now, what I have done is selected all of these surfaces and created a topological set called application surfaces. So that's going to allow me to very easily apply my boundary conditions without having to go through and click every individual surface. So when we do apply the pressure, I apply it to my topological set. So I'll just give you a quick demo of how you would do that. So if I've got select face as my selection tool, I could go in here and select all of these cylindrical faces and say topological set 2, create new set. So then you can select them all as one without the need to go through and individually select them for boundary conditions. So the pressure, this CSV file corresponds to the pressure loading that I showed you in the presentation earlier. Now the same goes for the internal thermal load. So this is the temperature applied to the application surfaces, and then after 0.1 seconds we then go back down to the lower temperature of 360 Kelvin. Now this doesn't mean that then the temperatures on those surfaces are going to actually match these temperatures, because we've applied it as a film coefficient, so a heat transfer coefficient. So that means that these are reference temperatures for this heat transfer coefficient. And what I've said is we're going to apply a very, very strong heat transfer coefficient up to the point of 0.1 seconds. So at that point, then all of the temperatures given in that thermal shock data are going to be experienced on the application surfaces. Now, after that, I'm going to go down to a very low convective heat transfer coefficient. And so this means that actually the temperatures on the surface are going to be able to change because we're only using a heat transfer coefficient rather than applying fixed temperatures. Okay, so that means we're going to be able to see the temperature response on those application surfaces. If we applied this boundary condition as fixed temperatures, we would only ever see the temperatures on those surfaces that we apply. But if we use a heat transfer coefficient, we can actually then see the temperature response on the application surfaces themselves, because we're using a very low heat transfer coefficient after the 0.1 seconds of thermal shock. So that is almost it for the setup of the simulation. I would go into the simulation control, which is where you can utilize the cloud capabilities of SimScale. So we can use up to 64 cores to run our simulation on, and then we can also specify how long we want to simulate this simulation. So I'm only going to simulate up to 0.5 seconds. And so that's going to go after the thermal shock up to 0.1 seconds. Then we're going to look at the response for the next 0.4 seconds. And but obviously, if you're interested in the thermal response up to 10 seconds or even further, then you could just apply a longer simulation interval here. The time step is important to make sure that we that we resolve all the detail of both the loading and also the response. So that loading, we know that it's a very steep gradient, so actually we need quite a small time step to resolve that accurately. And then afterwards we can increase our time step a little bit more because the thermal response is going to vary relatively slowly. So it's not going to be as abrupt as that thermal shock. So we can have a slightly higher, larger time step and still get the full response of the structure. And then that's it. All you would then do is run the simulation under here, click run, and start your simulation. Now I've got a summary of the results that I'd like to show you in, so I'm going to jump back into the presentation. So if we compare these temperature results, I've taken average temperatures on the application surfaces. So this was done using a result control. I'll really quickly show you how I did that because that is definitely important for you guys to see. So under result control, I know I'm interested in the temperatures on the application surfaces. So I'm going to apply an area average. So I've applied area average temperatures to those application surfaces. So I can use that same topological set to apply result control. So this means that during the run, we are going to, for our 0.5 second run, it's going to actually print out the results graphically. So we're going to see our average temperature over the full simulation. Now the same goes for, I've applied a result control for the principal stress as well. So I'll show you that later, but that was done in exactly the same manner. So an area calculation of average principal stress. And now I've taken the minimum component of the principal stress, which would correspond to the maximum compressive force. So back onto the results. If we look at that temperature response, we can see it is very different to the temperature load that we applied. The temperature reduces nice and slowly, as we would expect after the combustion and the experiment occurs. So this is an example of the animations that you can get out of the online post-processor with SimScale, and so you can really see how that temperature evolves over time, and you can really see which points on the structure the cooling process happens the quickest. Now, if we want to have a look at the stresses, the mechanical stresses, it's important to find the areas in which the stresses are concentrating. So during that combustion, up until 0.1, not only are we getting that applied pressure, but we're also getting that applied mechanical stress induced by the thermal shock as well. So that goes for after the thermal shock as well, but at the end of that thermal shock is the point where we're going to have the highest level of mechanical stress. So on the right-hand side, I've got a still frame of the mechanical stress, or the von Mises stress, at the 0.1 seconds. And we can see that the stress really concentrates on the rim of the brass piece. And if we have another look at another area in the model, we can see that the stress is also concentrating on the exposed edges of the internal combustion chamber. Now, this might highlight a need to, for example, put fillets on the sides of these edges to reduce that stress concentration, or because with these sharp edges, it may actually be that crack propagation may occur. And so these are definitely pain points in the design that need to be taken care of. So we would look in the post-processing to see where that stress is concentrating and where we might need to make some iterations to our design. Now, as I mentioned, I also took in an average of the principal stress. So what we have is the minimum component of the principal stress over the 0.5 seconds of simulation. Now that minimum principal stress is the maximum compressive stress. So this is saying that the finite elements on the application surfaces, so those with that first layer of elements on the application surfaces are under very, very high levels of compression. So we're seeing extremely high principal stresses during the combustion, but unless we've got stress concentration, for example, on those edges, those principal stresses are not going to be too much of a concern because they don't go through the full thickness of the structure. They're only on the surface, these application surfaces. So I think we'd be pretty confident that this thing's not going to break apart, but we do have very high principal stresses. So for something like fatigue analysis, it may be very important to check these maximum values and see what the life of this for exactly the surface elements will be, because it may be that over time the surfaces, these steel surfaces, are really going to deform and they're going to get some very strange shape deformation, which may mean that the combustion chamber can't be used as effectively as when it was first designed. So this is the quantitative data that you can pull out of your simulations, and if you really want to see where the stress is actually concentrating, then we need to look, for example, here where we look at animations and at shading of the different stress components in the model. Now that is all I had in terms of results that I wanted to show you, but I would like to ask if anyone has any questions regarding either the setup, the simulation types, or in general about the structural capabilities of SimScale. So if you do have any questions, please just type them in under questions on the GoToWebinar panel, and I'll do my best to answer them. Okay, I've got a question from Rishi about how do we check the mesh metrics. So how so we want to see how the mesh quality is. So what we can do is we create our mesh up here, and if we want to know how good our mesh quality is, that's all hidden down in the meshing log. So if you want to go into the meshing log, head to the end of it, you're then going to have an impression of the aspect ratios and the volume ratios of the tetrahedrals in this mesh. So our new surface mesher is based on tetrahedral elements, and so ideally we're looking for aspect ratios down towards 10 or 20 would be ideal, but under 100 is not too bad at all. So another question I would like from Hichem. I would like to know if it is possible to couple flow with the structure to determine the input for FEA. So as you can see, we've got so many different types of simulations on the platform, and of course we can take our CFD results as surface averages from a CFD, just like I did under result control here. I created an area calculation, an area average for the temperatures and the principal stress. You could do exactly the same for the pressure forces in a CFD experiment, simulation, apologies. And then we could bring that in as a boundary condition, as a surface boundary condition in our FEA analyses. So that wouldn't necessarily be a thermomechanical simulation type, but you could do that, for example, in a heat transfer unit or a cooling system where we would simulate the thermal behavior of both the fluid and the structure using a conjugate heat transfer simulation. We could then take those temperatures as surface averages and then bring them into a thermomechanical FEA simulation. So then using and you could do that all in the same project. So under here we could add a conjugate heat transfer, and then we can add another thermomechanical simulation, and then you'd have the full feedback for your structure. So you're going to not only see the fluid behavior and the temperatures in the fluids and on the structures, but you're also going to see the mechanical stresses induced by those temperatures on the structure itself. Okay, can we import our own materials, or do we have to make a CSV file? Can we do topology optimization? Wow, lots of questions in one there. Okay, so in terms of importing your own materials, what you can do is customize the materials that we do have. So in our materials library, we could go to gold, and then you could customize the material yourself. When you are applying a plastic stress strain curve, you're going to have to apply it as a CSV file. And so topology optimization is not something we're currently pursuing, but if you are interested in taking your simulation results to optimize your geometry, we use a more traditional approach that you would then feed back into your CAD system and then bring in a new design and resimulate using the same simulation settings. You'd be able to quickly turn around another simulation for your new design. But we haven't optimized this process for topology optimization. Okay, well, thank you very much, everybody. I think that's all the time we have for today's webinar. It's been a pleasure talking to you all, and we'll hopefully see you again here for another SimScale webinar. Okay, thank you very much.